Hello, we're the Hadoop infrastructure team at Bloomberg, and I want to present to you some of the patterns that we've come across this last year that have really been interesting to us at our scale. Myself, I'll be presenting along with Amit Anand and Bijounaire from my team. So with that, I want to just let everyone know everything we present today is up on github.com. You can go look at it at github.com/bloomberg/chef-bach, or you can find us on Freenode. With that, I'll hand it off to Amit to talk about how we build our clusters.
Thanks, Clay, and thanks everybody for joining us today. So I would like to start with what does a Hadoop cluster look like at Bloomberg, or a Bloomberg clusters. So at Bloomberg, we build two different clusters right out of the box from our current Chef stack. So these are Hadoop clusters and Kafka clusters. And these clusters have environment-specific requirements and application-specific requirements. So application-specific requirements are basically tuning configurations and configuration for the Hadoop cluster or Kafka cluster. And environment-specific configurations are networking layout. Some of the clusters run on single NIC, some are running with multi-homing clusters, and some of them are bonded NICs. And on the storage side, Hadoop clusters run with just JBART, but Kafka clusters can have RAID 1 or RAID 10 configuration for the storage. And with that, and these clusters are built very regularly. And ever since I joined Bloomberg, I have been building a cluster every other week. So that is the frequency we have for our cluster builds. Every cluster in Bloomberg runs with a dedicated Bootstrap host. And Bootstrap host manages the entire cluster stack. And the Bootstrap host runs in a virtual machine, but it manages a bare metal cluster. And every Bootstrap server runs a dedicated Chef server for the cluster. So next thing is, why do we do a VM? So our VMs they have very lightweight prerequisites. It runs with a 4 GB of RAM and around 10 gig of storage. And with that approach, we can deploy multiple VMs on a machine, on a hypervisor host. And with that, we can manage multiple clusters from a hypervisor host. And we use Vagrant to bring up these VMs. And we use Vagrant to reconfigure these VMs. And this provides us to do a rapid deployment for our Bootstrap host. And it also allows us to easily relocate these virtual machines to any other hypervisor host if we need to. Now let's look at some of the services offered by our Bootstrap host. So our Bootstrap host serves app repository, some Ruby gems, some static files for Chef. It also offers Hadoop repository and Kafka repository for cluster builds. It runs a dedicated Chef server. It also runs a Kerberos KDC server for security of the cluster. And it also runs a Pixie server that we use to Pixie boot all the hardware machines and install OS on them. And we use Cobbler for that, and our code is available on the URL mentioned on the slide. And our Bootstrap host also provides bridge networking for the virtual clusters. So if you go to github.com and download the ChefBach code, you can build a VM cluster right out of the box. And it also provides us a way to strongly isolate each Bootstrap host. If any of the Bootstrap hosts goes down, it won't impact any other cluster. It is only tied to one cluster at a time. So now let's get into how do we build our Bootstrap host. So as I mentioned, we use VMs, and we use Vagrant to bring up this VM and reconfigure them. So we have a Jenkins process running in-house that basically builds a generic box image, and it configures the generic box with a dummy IP address and some dummy environment, data bag, and node and client object. So that's a fully configured Chef server running inside a generic box image. So we take this box image and we move that to a hypervisor host. And after that, we use a specific environment-related JSON file that is parsed by Vagrant. And that JSON file is the single source of truth for the Bootstrap host as well as for the entire cluster. And with that JSON file, the first thing we do is we reconfigure the network on the Bootstrap host. As it came from Jenkins and it had a dummy IP address, now we need a way to reconfigure the network so that it can talk to a particular cluster. So once that is done, then we configure the knife.rb on the Vagrant machine so that it can talk to the right Chef server. After that, once these two pieces are configured, now we need to reconfigure the Chef server itself, because Chef server has multiple components and they are tied to that dummy IP address. And we use Vagrant to reconfigure all the components using shell provisioner, and we reconfigure the Chef server. And next step is, since it came from Jenkins environment, it had a dummy IP address, it had dummy objects like environment, data bag, node object, client object. We need to clean them up as well. So for that, we make use of Chef REST APIs. And finally, we convert our Bootstrap host to be an admin host. because that is really required to upload any secrets like SSH keys, database passwords, or Kerberos key tabs. So this is an example where we're using Chef Solo Provisioner inside Vagrant. So in this case, what we're trying to do is, the first step is to configure the network. And this Chef Solo Provisioner is going to run inside Vagrant file, and it's going to go and talk to the virtual machine and configure the networking environment reading from the JSON file. The key piece here is the Chef Solo Provisioner in Vagrant. It expects all the Chef code to be available on the hypervisor host. Any recipe that you want to run inside the virtual machine, for Vagrant to take that recipe, it needs to be available on the hypervisor host. But since we build our generic box using Jenkins, and it bakes in all the repositories into the box itself, like Hadoop recipes and Kafka recipes, we needed a way to figure out how can we talk to the virtual machine directly and pick up all the recipes from there and run it inside the VM itself. So for that, we had to go through a lot of hacks and go through all the documentation, and there was no documentation available how you can make Vagrant talk to the virtual machine itself and pick the file inside the VM. So after reading code, we did a lot of investigation, and we figured out that there's a special way we can pass the parameter. So if you look at Chef environment's path, so that is passed as :VM, empty string. And similarly, we have environment name. Environment comes from JSON file. Similarly, cookbook path is passed the same way, and roles path. But finally, we have chef provisioning path. So that is the location for all the recipes and cookbooks inside the VM. And when Chef Solo Provisioner is executed, it's going to go to this provisioning path and read all the recipes that is specified in the chef add recipe call. And it will configure the network. And after that, now network is configured. Now we need to configure Chef server. And since Chef server has multiple components, we are using Chef Solo Provisioner to reconfigure the Chef server. And so this is the next step in the building Bootstrap process. Now the network is configured, and we have Chef server configured correctly. Now we can talk to Chef server. Now we know the IP address of the Chef server, and now we can talk to it. And to do that, we need to clean up all the environments, data bags, and also we need to clean up any existing node and client objects. And to do that, we are making use of Chef REST APIs here inside a recipe that will talk to the Chef server, and it will go and delete any existing environment, any existing data bag, node, and client objects. So now Chef server is cleaned. The next step here is we need to convert the Bootstrap to be an admin. And to do that, we again use the Chef REST API, and we set the admin flag to true on the Chef server for the Bootstrap host. Now this Bootstrap host can upload any secrets to the Chef vault or data bag. So once that is done, now we configure the Bootstrap host, and now we can pixie boot all the machines, and we can install all the software on the cluster. Cluster will be up and running. But now the question is it really ready for use? And the answer is no, because building a cluster is one thing and using a cluster is another thing. And to use a cluster, we need to make it usable. And to make a cluster usable, we need to deploy code on it. And this code can come from our tenants that use the cluster, or some application cookbooks that either they're developing or we are developing for them. And similarly, we need to deploy some Ruby, which are really important to interact with the cluster. And the key gems here are Zookeeper and WebHDFS. And since these clusters are not single machines, we need to figure out, and there are multiple daemons running on multiple nodes, and some of them are single daemons and some of them are multi-master. Now, in case of multi-master, we need to figure out where the active daemon is running and where the standby daemon is running. So all that is done through Zookeeper and WebHDFS providers. And with this situation, idempotency and handling race condition is very critical. So let's look into an example, how we deploy code to HDFS. So HDFS is a distributed file system inside Hadoop. And so this is a process where this is how we onboard a user onto Hadoop cluster. And the process involves creating a user directory on HDFS for a user and setting the right permissions for that. And to do that, Chef is very good at creating directory on any machine, but Chef is not aware of any HDFS file system or any other distributed file system. And to achieve that, we had to write a provider for Chef's directory resource. So our provider, what it does is it takes the Chef's directory resource and it overrides the provider for that and goes and creates a directory on the HDFS instead of local machine. And the code for the provider is available on the link mentioned on the slide. So this is another example how we deploy Kafka topics in case of our Kafka clusters. So Kafka topics are required to be able to send and receive messages. And to do that, what we have done is we created our LWRP. And so this is an example of this is the resource on the slide that you can see with some attributes. So you can specify the name, partition, and application for the topic. And then you can create you can create any topic on the Kafka server. And it will automatically go and figure out where the right zookeeper is running for the Kafka cluster, and it will create the topic. And next is Kerberos. So Kerberos is the security system on our clusters. And to talk about that, I will ask Clay to join me.
So Kerberos came out in the 1980s, but it's still the standard way to secure clusters of machines. It's usually known as kind of a beast to configure. Some of the places where Chef really helps us is the fact that on our machines, we could be running maybe 10 services per machine. And say on a 50-node cluster, that could be 500 key tabs, pieces of cryptographic information that we need to maintain. And so that gets difficult to do, but with Chef, it's really nice and easy, especially with Chef Vault to be able to encrypt that so that you hopefully don't lose that information. Similarly, multi-homed hosts. Again, a big nightmare in Kerberos, because quite often you end up doing a reverse IP lookup on a host to figure out, is that the right host or is someone impersonating that host? And in the Hadoop ecosystem, they've had this shim for quite some time, so you can do _host, and it imputes the host that's running. The problem is, on a multi-homed host, what IP address do I use? So with Chef, at least we can say, that IP address should be used here, this NIC should be used there, and we can actually go and do that definitively. However, there's still challenges. So the providers, as pointed out, we use both Web HDFS, and that has a Spinigo authentication. It's an API for being able to actually do that Kerberos exchange in an HTTP request. But now the problem is, how do I authenticate? If we're running Chef as root, I can use all of the systems role accounts. But if I'm not root, if I'm a user process that's running Chef unprivileged, or if we're deploying tenant code for which we just don't have that key tab, then how do I actually specify that? How do I make sure that I know which key tab Chef's using? And that becomes a little more difficult. Today, there's not really any great patterns that at least we've seen in the Chef ecosystem for being able to do that. You can see all of our Kerberos code, however, at this URL. With that, I'll hand it off to Bijou, who will talk about how we do wrapper cookbooks for being able to shim in kind of some of the custom cluster stuff that we do.
Thank you, Clay, and thank you all for joining us. Before I go further, there's a lot of, the coming slides will have a lot of code in it, and that's been edited to fit into the slides and this talk. So please heed to this warning. And also for this section of the code, you can see the complete code on the URLs provided. So once you have the slides, you'll be able to go and look at it. Logic injection. Looks like it's a catchy headline. What that means in this context, we use community cookbooks, and I'm not sure if there's anybody in this room who doesn't use the community cookbook. And community cookbooks make the using of Chef so fun. And I would thank anybody and everybody who has contributed to community cookbooks. The community cookbooks as a standard is very good at installing a software, configuration, making changes to the configuration file, and then starting the service. But there's some challenges in our environment, as you might have gathered from the slides and the talk from Amit and Clay, that we are dealing with some distributed components. So we would want to, as part of the installation and the configuration and the starting of the service process, we would want to be able to inject some logic to determine a service can be restarted or not. So that's one of the problems we have. So for example, HDFS, if anybody knows about it, we want to make sure that all the nodes, the HDFS service on all the nodes doesn't come down at the same time. So we want to make sure that when any node is trying to start HDFS service, it finds or it determines some or goes through some logic to determine whether it can restart it or not. So that's pretty much what we want to inject. Few ways we can achieve it is by, say, create our own cookbook, or request the community cookbook owner to change the cookbook to include our logic, and these are all not options which is preferred. So we came up with a simple solution. So let's look at the code. What's right now there is a condensed version of the community cookbook recipe where the installation happens, and there's a template resource which would configure the required configurations, and it does the service start and service resource to start and restart of the service. So this is standard across all the community cookbooks. So if I have to determine a logic before the service gets restarted, then I need to inject some logic between the templates resource and the service resource. So that is the key. So before I move on to say how the solution was implemented, I just want to point out that just keep in mind about the template resource and the notification. It restarts the service Kafka in a delayed mode. So just keep that in your mind to follow through. So what the change we wanted to make, or we want to do in the community cookbook, so that the community cookbook still stays generic, but still it allows a user to wrap on it so that they can inject a logic. So what was done is remove the service resource from this recipe, from any community cookbook recipe, and then replace it with include recipe function that, and then which would point to a node attribute which stores a recipe's name. So that is the change on the community cookbook recipe. And also note that on the template resource, now it is, instead of it's notifying the service resource before, it notifies to a Ruby block. And also it does the notification to create immediately. So that is a change in the community cookbook recipe. So as I said, what are we including? The including is, what is the recipe is going to look like, which we are including instead of the service resource. So this is how the recipe looks like. So again, the first step is a Ruby block, which the template resource is currently now notifying, and then the original service recipe in itself, sorry, the service resource in itself. And remember that, as I said, before you have the template resource right now is doing an immediate, but on the new recipe, we are doing a notification. What it was, the notification is delayed, what it was as in the original community cookbook recipe, where in the template resource we had notification as delayed. Hope this gives a solution. So okay, this changes what it would do is, it would make sure that the community cookbook stays generic, and it allows wrapper cookbook to be able to inject logic. So let's look at how a wrapper cookbook can inject the logic. So in the wrapper cookbook, what we can do is we can create a recipe. The only requirement is that it has the first step to be same as the recipe we created in the community cookbook, which is nothing but a Ruby block. And then after that, you can include any logic to do, like for in our case, doing a restart of the service, or determine whether the service can be restarted. And then the service recipe in itself, service resource in itself, and the last step being any cleanup you want to do after the service has been restarted. So in our case, what we do is any node which wants to restart, it needs to acquire a lock, and that is the logic which we implement in between the Ruby block and the service resource. And when the service has been restarted, it cleans up, and the cleanup process is to release the lock so that any other node can go and restart the same process when the restart requirement is there. So this is the way we handle this logic injection into a community cookbook. Next is service on demand. We have common set of services running on all the nodes in our cluster, and we want to be able to get the application users to be able to request for the service on demand whenever they want it, but free of cost though. So what's happening is, in our case, for example, one of the common services to be able to copy logs from the different nodes into a into a common location. So for example, you can appreciate that we have so much nodes running HDFS or HBase or whatnot. And if there's a problem, then if you want to look at each node, then people have to go across nodes and look into the logs. So this way, if the service requests for a copy of its log into a common location, they can subscribe to this service and they will be able to copy into a common location. For in this case, what we use is the common location being HDFS and the common service being Flume. So let's look at how we achieve this this kind of an on-demand service request. So we have a node attribute which is a hash of hashes, and it expects data to be in the form of the data structure provided below, which specifies what's the log file to be copied and whether we want to do a copy or not, and a unique identifier so that we know which application has requested for that that feature. So this needs to be added to the node attribute. So how does any service, like for example, HBase, want to request, or any application who wants to be able to copy the logs created by that application to the common location? So in its own recipe or the application recipe, what any application user has to do is to specify or build this data structure and add to that node attribute, saying that what's the log location and whether they want it to be copied or not. So as you can imagine, in a node, there will be multiple services which will be running, and any application service which wants to do this, they include that in the recipe, and depending upon what's being defined the role, it gets executed, and then it gets attached to it gets appended to the node attribute. So what does the common service do? The common service recipe, what it will do is it walks through the content of that attribute and then builds the required configuration files and starts the service. In this case, since you are using the Flume, the recipe for Flume would walk through that data structure or the attribute and the data structure and creates the Flume agent configuration files. And then what it does is it starts the Flume agent for each of the requests which is on the node. So in this way, in the future, when there is new services being added to our cluster, or if any new applications comes into play, and if they want to make a request for copying the logs into a common location, they can dynamically add to the recipe, and it will be taken care in our cluster. So a similar requirement, but in a different way, is pluggable alerts. It's again, in our environment, we have monitors being executed, or monitoring being done on various parameters. It's a big list. As you can imagine, JMX parameters and server parameters and whatnot, and they all get collected and stored in a common data source. We also have an alerting system, and it has its own agents to be able to collect these same statistics. But since we are already collecting the data into a common data source, we didn't want to reduplicate this effort and be able to and waste our node resources. So the thought process is we will be able to pass the required data from the data source into our alerting system, and then we will be able to create alerts on the alerting system. So we want it to be flexible and dynamic, because we will be creating more alerts, or we'll be monitoring more parameters, or we'll have more services which we need to be monitored. So we want it to be flexible. So again, the pattern here is using a data structure in our node as a node attribute. What we can do is any user or any new alerts you want to create, you can specify the query to be run against the data source, which would pull the data on which alerting has to be made and send it across to our alerting system. And in the alerting system, there's another set of parameters which we can define, and it would create the criteria in our alerting system so that alerts are created for that particular parameter which we are interested in. So it's a little change. It's a similar requirement, but it's for data instead of services like what we thought the last time, and the last section. So as we did a lot of the work, and there were a few pitfalls we came across as well. And this one we want to highlight something to you, something to be watching out when you are using templates with providers. So you want to make sure that we use the cookbook attribute for templates when you're using providers, when you're using providers, templates with providers, and you can use the new resource.cookbook. You want to definitely use that. And there's an Poise template helper you can look at. That's one of the lessons we have learned. And the next one is about library function calls in wrapper cookbooks. So the scenario is like this. We have a community cookbook, which is Cobbler, in this case, which provides a provider, which expects a template to be passed, a pre-seed file template to be passed as a parameter. And in our wrapper cookbook, in our case, we have a function call. So just to show you in a code, this is the wrapper recipe which we are using, or a section of the wrapper recipe, which calls that Cobbler cookbooks provider, and then we are passing the cobbler.bcpc ubuntu host.preseed as a template. And in the template, in the bottom, you can see that the template has got a get config function call, library function call. So it was all fine and working, but at some point we want to move into the best practices of Ruby to modularize the library functions. So what happened? We added this thinking that including the BCPC OS helper, which is the module library, would help us identify the function call in the template, but it didn't happen. It blew up. So just the lessons learned is when you are using any config library, the function libraries, you may want to fully qualify it so that you don't get in the same situation. Yeah, this issue was found by using the Cobbler cookbook written by Clay, and I would pass on to him to talk about some of the pain he had gone through.
Yes. So the last patterns we saw were all very data-driven instead of resource-driven or anything like that. As we moved on, we created RAID arrays through Chef, and we had dynamic resources that kind of came into play. So you can see here we've got a Ruby block, and that Ruby block creates both some directories as well as an execution provider. And one of the challenges there is the fact that these don't enter the run context. These also are not as obvious to be able to reason about because they may or may not be called. If there's a guard attribute on these Ruby blocks, those resources would never be created in that Chef run. And so one of the challenges becomes, how do we want to actually deal with this type of heavyweight system configuration? A RAID provider, a RAID controller, is a complex piece of equipment. We could have, say, 14 disks on one machine and maybe only 4 on another. And so traditionally, our recipes would just take that as an attribute, but that required a human to know how many disks the machine had, and that's just not right. So we had a question, do we do this all in compile time? Chef, of course, is split between compile and converge. So normally in compile time, you might install a Ruby gem, and you might use that in your converge phase. Quite often, the Zookeeper gem, for example, we would install in compile time. It's lightweight. It's relatively straightforward. But configuring an entire RAID array, installing the software packages, being able to actually change all of our disks, having to rerun OHI, all in compile time seemed a little strange, a little heavyweight. So if you do it in converge time now the problem is you have these Ruby blocks running around that have to create all of these resources, and it encroaches on your wrapper cookbooks and all that, because now you can't use a community cookbook that assumes you can tell it where all your mount points are, for example. So some challenges here is you don't update the resource collection in Ruby blocks, and you end up with lazies everywhere. And even that has some challenges. Lazy is really nice. If you want a converge time check on one of your guards, that gets a little less nice. Lazy creates a delayed executor, and one of the challenges with that delayed executor, anything that's not false in Ruby, is true. So your guard is always true. Well, if you want that delayed executor to actually return a Boolean value, you probably ought to call it. So here you can see at least how we got our lazies to work, but definitely not as clean as one would hope. With that, I'll hand it back to Bijou for how we do single machine service restarting.
So this is a scenario which may come up in different ways. For example, when you have a service which is dependent on multiple other services, what I mean by dependent is, by an example, like you have a monitoring service which monitors multiple other services. And that's what I mean by dependency in this case. So it's not tightly coupled, but at least when there's a restart of the process is being monitored by the monitoring system, there may be a need, the monitoring system has to be restarted. In this case, we used JMX trans. The older version required the restart. The latest version doesn't have to be, but I think at least this pattern can be used in a similar situation where you have services depending on multiple other services. So how do I restart that service, in this case JMX trans, when one of the dependent services is being restarted? So, oops.
There you go.
Okay. So again, you might have heard so many times I'm talking about data structure. Here again, we have a data structure which we include in our roles, so that it defines all the services on which the JMX trans depends on. So the key to note or remember about is the service name on which the JMX trans is going to be dependent on, and also an identifier or a string which can identify any process which got started by that service. So that's two pieces of information. We could keep it. And if there is any other new services coming up, which is going to run in this node, then users can go ahead and update this data structure. So what happens? So when in the JMX trans recipe, what will happen is it will walk through that data structure, and then it stores the service names in an array and all the strings which can identify the process of the array in another hash. And then, as you can see in the service resource in the JMX trans recipe, what we have built, that subscribe has been will be populated, or different lines of subscribes will be created for each of the dependent service for JMX trans. So in that way, if there's any of the dependent service get restarted in any chef client run, it gets the JMX trans gets restarted. That's fun, and it's straightforward in this case, since Chef gives us that kind of a primitive. But what happens if any of these multiple dependent services gets restarted from externally? Say, for example, an admin went in and restarted, or Upstart bounced that service. Since we are dependent on this JMX trans to do our alarming and alerting system, we want to make sure that JMX trans get bounced again. So as you can see, we have created a library function so that we can achieve this or we can have this capability in our cluster, so that if there's any of the processes get restarted, then we will be able to restart JMX trans as well. So this is just a quick snippet of that library function. So it takes three parameters. The one is the process name, in this case JMX trans, and process command, or it takes the string which identifies uniquely any process started by JMX trans. In this case, some identifier like JMX trans.jar or something like that. And the third one is the set of or the hash we saw in the previous slide. The process identifiers for all the dependent processes. So what it does is it finds the start time for the JMX trans service, and then walks through the hash of all the dependent services. In this section, it walks through all the dependent services, and then what it does is it gets the timestamp for each of the processes, dependent processes, and then compares whether any of the processes has been restarted after the JMX trans has been restarted. And if that's the case, it returns true, so that JMX trans can be bounced when there is when any of the dependent process has been restarted. And one thing I want to show here is we loop through all the dependent processes, even though we can return true if one of the process has been restarted after the JMX trans, is because we can identify which all the process got restarted in our logging. So this is how we manage the restart of a service which is multi-process dependent. And having said that, I want to hand it over to Clay to talk about a rolling restart function, what we have implemented in our clusters.
So one of the things that we tend to do is actually converge our machines automatically every 5 minutes. I think a lot of folks I've talked to here at the ChefConf go, but my orchestration framework can do, and that's fantastic. In our case, we want our machines to try to be as self-healing and as kind of tightly coupled to themselves only as possible, so we automatically converge every 5 minutes. So with that, we have some challenges of rolling restart. As Amit pointed out, the daemons themselves can have high availability. Maybe I have my data written 3 times to 3 different machines. I've got my data served by 3 other machines. And now the question is, if I roll a configuration change out and I have a 600 node cluster, I'm restarting a machine every 10 seconds. I might be bouncing a daemon or something like that. I'm very likely to hit a case where my data may still be unavailable. So we actually implemented a system whereby we can do a rolling restart and make sure that those machines don't all come down at the same time. Similarly, toxic configuration, maybe I'm linting my configuration files, somehow verifying them, but I still push something that just doesn't work in prod. And I start causing daemons to fall down. As long as they fall down and we can catch that, then we can stop this process from letting new daemons reconfigure. Now, one of the questions is, how do we actually verify this? So we can ask maybe a master daemon, how many slaves do you still talk to? How many have gone down? How many are up? How many do you expect? But that's got some delays. That's got some challenges. You still have to have a protocol that actually does report in. And then similarly, this becomes kind of a question of synchronous communication, something that Chef, at least across a cluster of machines, isn't necessarily designed to do with Solar that's eventually consistent. And then similarly, this is now starting to look like a locking problem. So with that, we have to kind of question, how do we want to do flagging? Do we want to say that, hey, yeah, I'm going to flag when machines appear to be down, but now there's uncertainty and there's a lag time there? Or do I take a deterministic stance that says, I only know when a machine explicitly says it's going to go down, and I positively flag? And that's actually the approach we took. There's similarly a question of deadlock avoidance. So if my cluster thinks that it can't reconfigure, but I have to reconfigure to get my cluster to think that it can reconfigure, well, that's a problem. So in our case, we actually have just a simple override. If it gets to the point where for whatever reason we're deadlocked, that requires one of us to step in and flip an attribute and say, hey, look, we're just not going to roll this out. Please restart. Similarly, there's a question of contention. Because this is a locking problem, if I take that lock using the pattern Viju explained earlier in a wrapper cookbook, for example, and I say, cool, I've got that lock, and I'm going to restart, that's easy. If I don't have that lock and I need to restart, well, do I pull and wait and just hope that I'll acquire that lock? Now my Chef runs might time out, or I might not be able to actually push new configurations because my Chef client's just sitting there spinning. Similarly, I can fail the run, but now our metrics blow up because I have hundreds of nodes sitting there saying, hey, I can't reconfigure, I'm going to abort. Instead, we can actually simply skip that service and go on. But now we have some state problems. We have to keep the state that we want to restart the daemon because we might not be changing that configuration file. We may have already applied that configuration change, and we just now need to restart. Similarly, it breaks the assumption of a procedural Chef run. If I look at, OK, I'm going to restart HDFS, and then I'm going to restart HBase, well, if I skip restarting HDFS, what effects can that have? Luckily, that seems to, from our perspective, be a much smaller state space than having to think about the matrix of all these dependencies across all of our machines. So we went with that. We think we can deal with the issue of breaking that assumption of a procedural Chef run or otherwise try to serialize that. With that, a lot of these patterns that we've talked about, from the multi-service dependency pattern to this rolling restart, start to look like primitives we just wish Chef had built in for clusters. And so here we have a definition, if I recall right, that is called Hadoop service, and probably should be called rolling restart, but Hadoop service. And here it's Zookeeper. So with that, I've got Zookeeper dependent on a couple files, and I give an idea of what that process is, both so I can make a lock and just recognize that process. So again, I use Zookeeper also, though, for the locking and for that synchronous communication. It's built really well for that. We deploy it on our clusters anyway, so we may as well take advantage of it. But now we have some issues with that. I might be restarting Zookeeper, which is holding the locks for if I'm restarting Zookeeper. So again, that availability is required, or that flag to skip. This is all based on a pattern from the Jenkins cookbook. At least that's where I saw it first. I'm sure it could have been implemented before then. Wait until ready, which used to poll Jenkins for if Jenkins was available, and if not, it would fail the Chef run. And in this case, we do that for Kafka by querying, again, Zookeeper to see if it's registered. If Kafka hasn't registered in Zookeeper, it's not probably alive, and so we can fail that run. And we do this for other daemons in other ways. The future directions of this are really cool. Our clusters are topologically aware. I can actually restart a rack at a time. Similarly, we might have some data on a cluster that's nice to have, but not necessary to have, and other data that's highly available and requires more care. So then I can start actually doing my Chef converges in a data-aware manner. And these are directions we haven't yet gone, but we look forward to. So with that, I'm sure everyone here is hiring, but we are as well. Jobs.bloomberg.com. If you want to join my team in particular, Hadoop infrastructure engineer or DevOps engineer for search infrastructure, we definitely welcome questions. Check out our code or grab us on Chef Bach on Freenode. And we look forward to questions now. Thank you, guys.
Okay, we're running into a break, but we can take a couple questions. Got one here.
Yeah, I'm just curious. You have a Chef server per Hadoop cluster. How do you bring in the overall set of cookbooks and recipes and environments for the non-Hadoop stuff?
That's actually a core part of how we build that Chef server. Is it's built in a Jenkins environment that it can talk to the internet. It can do functional testing on that Vagrant image, that Vagrant box as it's called, that we actually then deploy. So all of that just gets downloaded through right now a terrible shell script, but we've got a pull request in to do Burks, and I think I'll commit that as soon as I get back to my desk. But yeah, to use just standard Chef technologies to pull the cookbooks down. Once they're deployed, it's more of a manner then of using actually Git to get all of our configuration on, and that's why we converge every 5 minutes. That converge of the Bootstrap node, as we call it, actually would pull in those cookbooks if we need. Hopefully that answers it. Skylar, could I ask for the mic real quick? Thank you.
What distribution of Hadoop do you use?
I'd prefer not to say. You can look at our code to see what we pull by default, but Biju's actually an employee of Hortonworks, so yeah. Kind of permanently on my team. Thank you for staying with us for so long.
Thank you.
Any other questions? All right, anything you want to add, Clay?
Thank you guys, especially everyone who's a community cookbook author.
All right, thanks, Clay. Thanks, everyone.
Thanks, everybody.